All right, it's 1 o'clock. Let's go ahead and get started. Good afternoon, everyone. How's everyone doing today? Good, stressed, yeah. It's that time of semester. I know. Speaking of that, we do have our midterm this Thursday, and so I do want to remind everyone of that one more time. And so the midterm is going to take place this Thursday. Remember, it's going to be an in-class midterm, and so there's no plans to offer it online. And so for those of you on Zoom, please make plans to come here to class on Thursday. Otherwise, you won't be able to take the exam. Just not a good thing. And just a reminder, the things that you can bring to the exam are your writing utensil, pencil, pen, whatever you feel most comfortable with, calculator, and a sheet of notes. And so your sheet of notes can be 8.5. It's an 8.5 by 11 sheet. You can write it or type it. It doesn't matter to me. You can write on both sides, and you can have anything that you want on there. And so I think what people typically do is they write kind of like little summaries of each section that we've covered, as well as maybe an example problem or two. You can put like a motivational quote, if it helps you perform well on the exam too. I've seen that. So, all that is good. The only thing you can't have on the note sheet is the exam answers, which is impossible because I haven't written it yet. And so, unless you can think of the exam before me, then that's not going to be on your cheat sheet. Okay. Okay, and so the study guide is on Canvas, and so I don't think I ever sent an email about that, but it is there. And so if you go to the lecture section, the lecture notes section of our files folder, the study guide is there. And so if you haven't taken a look at it yet, I would highly recommend that you do. Because it's just there to kind of help you guys study. It's to help you kind of narrow down what's really important and to kind of it almost gives you like a checklist to help you study, which I think is always helpful. Right? And then probably on Friday, probably you guys got the email where I recorded a review video. Okay, so kind of based on what I saw from the first 2 homework assignments, I've seen that I think the thing that people are kind of struggling with a lot are the non-standard cash flow conversions. And so what I did was I recorded a video where I went through problem 3 on homework 2. That was the non-standard cash flow conversion problem, and I basically just did the solution to that problem in very, very step-by-step detail, kind of explaining every step of the way. And so I would definitely check that out for the midterm, just so that you have that down pat. Okay. All right. Okay, so I think that's all my announcements. So remember, homework 3 is due tonight, and so make sure you guys are working on that. And since I want you guys to have the solutions for homework 3 before the midterm, you can expect the solutions for homework 3 to be posted by about midnight tonight, and so right around when it's due. Okay, just so that you can turn it in, and then right away you can have the solutions, and you can use that to help you study for the exam as well. Okay. All right. Any questions on any of this before we get started for today? Okay. All right. So let's go ahead and get started. And so last week, we kind of wrapped up what I consider kind of be the big three of economic analysis techniques. Okay. Oops. And so I'd say so far, we have covered okay. And so the first technique that we went over, when I say technique, I mean, the different methods that we have for actually comparing economic alternatives. And so the first one that we saw was present worth analysis. Second one that we went over was annual cash flow analysis. Okay. And of course, those are the two main ones that are going to be on the upcoming midterm. Okay. And the one that we covered last week, which is not going to be on the midterm, but it will be on the next one, is rate of return analysis. Okay. So I'd say, those are kind of the big three. And so in terms of, techniques that you can use to perform economic comparisons, I'd say these three are three of the main ones that are used. Not only in their usefulness, but I think in the skills that they teach you in terms of doing cash flow conversions, balancing a cash flow diagram. These three kind of teach you kind of the spectrum of that stuff. And what you'll see, up until the second midterm, we're going to continue to build on the knowledge that we've developed here on this part. Okay. But with that said, there are some other analysis techniques that are out there that can help you in certain situations. And so in some cases, it helps to use kind of some of these other methods. And I've kind of grouped them all together into one lecture note because each of them by themselves are not that complicated. And so it's hard to kind of devote a whole week or even a whole lecture to them. And so I call this kind of all the other techniques. And so we're going to go over two such techniques today. And so you'll see that they kind of build almost directly kind of off what we've done. And understanding them, I think won't be too big of a deal. All right, so the first one that we're going to do is called benefit cost ratio analysis. Okay. And so the point of this analysis is kind of exactly as described by the name. So you're going to basically compute all the benefits, convert it all into the same form of cash flow. You're going to take all the costs, convert it all into the same form of cash flow, and then just take the ratio of them. Okay. Okay. And so it's always going to be benefits over cost. And I think, at least for me, I think you probably heard just kind of people just saying, nonchalantly about cost to benefits ratio, but we do benefits over cost just so that, if the ratio is over 1, that's a good thing, right? And so we want something over 1 to usually be a good thing. And so we can compute this in a few different ways. And so the only requirement is that you convert it all into the same type of cash form. Okay. But most commonly, you're going to do things like present worth or compute the EUAC or EUAB. Okay. And so the formula that we have is like this. And so we take the present worth of all the benefits divided by the present worth of all the costs. Okay. Now, the way we can do it is we can take the EUAB, which remember stands for the equivalent uniform annual benefits. And so that's all the benefits converted into a uniform series. Okay. Or the EUAC, okay, equivalent uniform annual cost. Okay. Either way is going to give you the same ratio. And so you can convert it to whichever form that you find the easiest. And then what we do from there is we compute its value and we see if it's greater than 1. Okay. So generally speaking, if your benefits are greater than your cost, you're going to get a value greater than 1, which is good. But then if you have a benefit to cost ratio less than 1, then that's a bad thing. So that means you're going to be spending more money than you take it. Okay. Okay. But actually very similar to rate of return, if you're actually going to use this benefit cost ratio to do a comparison, just like in rate of return, we have to do incremental analysis. Okay. And so remember, incremental analysis means that we take the difference. And so we take the difference between the higher cost option minus the lower cost option, and we do that across the board for all their costs and all their benefits. And then we are going to find the ratio of that difference instead. Okay. And so if the ratio of that difference is greater than 1, then we know that we have to go with the higher cost option. If it's less than 1, then we go with the lower cost option. Okay. Okay. And so when you find the ratio of the difference, if it's greater than 1, you want to go with the higher cost option. Okay. If it's less than 1, you're going to go with the lower cost option. Okay. So same idea as incremental rate of return. It's just that the calculations we're going to perform are a little bit different. Okay. Let me go ahead and let's look a little bit. Okay. Any questions on this before we jump into an example? Okay. All right. So let's do an example to see how this is done. And so in this example, let's say that we're comparing, or we need to decide between purchasing two machines. Okay. And so we'll call them machine A, machine B. Okay. I think this is actually a repeat of an example we've done before, but now we're going to do it with benefit cost ratio. Okay. And so if machine A has an initial cost of $10,000, machine A has a revenue of $3,000 each year. Okay. Whereas machine B is going to have an initial cost of $13,500. The revenue for machine B is going to start at $3,000. Okay, so that's a revenue in the first year. But in addition to that, the revenue is going to increase steadily year by year. Okay? And so we're going to have a gradient of 500 to represent the fact that the revenue is expected to climb or to grow by $500 each year. Okay? Okay. And so if we assume an interest rate, if we assume our interest rate here is 7%, and our analysis period is 5 years for both, okay. Let's use a benefit cost ratio to determine which machine to buy. Okay. All right. So fairly straightforward example. We have two machines here. They are very similar to each other, and so they both have initial cost. We're given the yearly revenue for both of them. The only difference is that machine B is going to have an additional revenue of $500 of gradient each year after the first. Okay. All right. And so just, normally if you're doing a comparison, you don't have to find the benefit cost ratio of each machine individually. But since this is our first time, let's find each individual benefit cost ratio and then find the ratio of the difference. Okay. Okay. So let's do machine A first, because that one is more straightforward. All right, so let's go ahead and take or compute the present worth of the benefits. And then compute the present worth of the costs. Okay. All right. And so the only benefits for machine A are the $3,000 revenue. And so we have $3,000. Okay. But this $3,000 revenue is a uniform series. And so we need to convert that to a present sum. And so we're going to do a P over A conversion. Our interest rate here is 7%. And then our N here, or time period, is 5. And so if we look up this value in the compound interest tables, this is 4.100. And so we perform the multiplication. We have 3,000 times 4.1. We get 12,300. Okay. So notice here, we only did this for the benefits. And so we're going to take the cost in a second. Okay, and so the present worth of the cost, the only cost that we have is the initial cost, which is already in present form. And so the initial cost here is already a P. And so we don't need to do any conversion here. And so the 10,000 is the entire present worth of the cost. All right, so now with both of these computed, let's go ahead and take their ratio. And so we have the present worth of the benefits divided by the present worth of the costs. Okay. And so we have 12,300 divided by 10,000. Okay. And so you punch this into a calculator, and what you get is a ratio of 1.23. And so, of course, that's a good thing. And so this tells the company that if they invest in machine A, the amount of money that's going to produce is going to make up for its costs. Okay. And so by the end of 5 years, they're going to earn a return on their investment. So it's not just going to be a waste of money. Okay, so now let's do machine B. And so we're going to repeat the same process. And so we have the present worth of the benefits, and then the present worth of the costs. Okay. So for machine B, we have two sources of benefits. And so we have the $3,000 revenue, which is a uniform series. Okay. And so this is P over A, 7%, 5. Okay. So that's going to be the same as machine A. And so that P over A factor is 4.1. But additionally, for machine B, we also have our gradient. And so to this, we're going to add 500. Okay. And we need to convert this gradient to a present sum. And so this is going to be a P over G, 7%, and 5. Okay. And so if we look up this conversion factor in the table, this is 7.647. And so if we add those two together, we have the 3,000 times the 4.1 plus the 500 times 7.647. We get 16,120. All right, and then just like machine A, we have the present worth of the costs. We only have one cost here, which is the initial cost. And so our present worth of that is going to be 13,500 with no conversion, because this is already in present sum format. Okay. All right, and so from these, we can compute the ratio. And so the ratio is just the ratio between them. So you have present worth of the benefits divided by present worth of the costs. Okay, so we have 16,120 divided by 13,500. And so we compute this, we get 1.19. Okay. All right. And so, again, if we're doing our comparison here, just doing the ratios of the individual options here is not enough. And so we're going to have to do the increment. But, I did want to show you each one individually first so that you have an idea of how this is computed. Okay. All right. Any questions on any of this? Okay. Okay. And so, from these results, it may seem like machine A is the better option to go with because you get a higher ratio there, right? And so it makes you think that, you're going to get more bang for your buck. But what we've learned already from, the past couple of weeks is that, if you do these kind of economic comparisons kind of individually, it can be a little bit misleading. So What we're going to do is we're going to take the increment instead. Okay. And remember, whenever we take a difference for these, we take the higher cost option first minus the lower cost option. Okay. But then we're going to do the same things before. And so we're going to take the present worth of the benefits. Okay. And we'll take the present worth of the cost. Okay. Except now we're taking it of the difference between them. Okay, so let's start with the benefits. And so for the benefits, let me use a different color here. So I'm going to use a green to denote machine B. Okay. And so machine B is the higher cost option here. And so we're going to list those ones first. And so the benefits for machine B are going to be a 3,000 P over A, 7% and 5. And then we have the additional gradient from the, or the additional benefit from the gradient. So that's 500 P over G, 7% and 5. Okay. Whenever I use green as a lecture color, my next instinct is to use red because it stands out from green. But then I remember some people are red-green colorblind, so they can't see it. So I have to like actively stop myself to not use red. Okay, and so now let's do the benefits for machine A. And so machine A, the only benefit we had, we scroll up here, was a 3,000 P over A. Okay, so we have 3,000 P over A, 7% and 5. All right. And so we can see from this equation here that that two of these terms are going to cancel out. And so in green right here, you see we have a 3,000 P over A, 7% 5. And then we're subtracting that exact same thing for machine A. And so these two are just going to cancel out. And so the only thing we're left with here is 500 P over G, 7% and 5. Okay. Okay, so now let's do the same thing for the costs. And so for the costs, once again, we're going to do a machine B because it's the higher cost option. And so machine B had a cost of 13,500, whereas machine A had a cost of 10,000. Okay. No conversions here are needed, and so we set 13,500 minus 10,000, and so we can do the simple arithmetic. What we get out from that is 3,500. Okay. Okay, so now that we have the present worth of the benefits increment and the present worth of the cost increment, we can now take the ratio and decide, which machine should we get. Okay. So just like before, we're going to take present worth of the benefits divided by present worth of the costs. Okay. And so for the benefits, we have 500 times P over G, 7% and 5. Okay. And then in the denominator, we have the present worth of the cost difference. And so that's 3,500. Okay. We know from above that this P over G factor here is 7.647. Okay. And so we have 500 times 7.647 divided by 3,500. We carry that arithmetic through. And what we get is 1.09. Okay. And so, what this tells us is that, because the ratio of the difference here is greater than 1, that means we should go with the higher cost option. All right. And so, this is another good example where, if you looked at each option individually, it may seem like you get, more bang for your buck for doing machine A. But if you went with machine B, that's kind of an overall better use of your money, because if you went with machine A, you would have a leftover $3,500 that you didn't spend. And then what this is telling us is that if we go with machine B, then, we would out earn that additional $3,500. Okay. All right, any questions on this example here? Okay. All right, and so that's the basics of benefit cost ratio, and so it's nothing really new, and so it's basically present worth analysis just with one additional step. Okay, but there are some variations on benefit cost ratio, and this is kind of where benefit cost ratio kind of tends to shine compared to some of the other methods. Okay, and so these are what I call variations on benefit cost ratio. All right, and so kind of the variation that is used on benefit cost ratio a lot is to account for public works projects, or in other words, projects that aren't really meant to make money. Okay. Because for these projects, they, consider things like working on roads, servicing the freeways, right? So things that, the government's not charging us to drive on the freeway, thank goodness, but they may someday. But the impact on these projects is not really measured in strict dollar amounts, but we can kind of measure their impact in other ways. And we can use the ratio to kind of see whether certain projects are worth it or not. Okay. All right, and so for these cases, we can modify our ratio where instead of just being the present worth of all the benefits or all the revenue divided by the present worth of all the costs, you can modify in this way. And so instead, on top here we can have the benefits and consequences for the public. Okay. Divided by the cost to the government or the cost to some sponsor. Okay. Okay. So this is used a lot, for a lot of government spending for a lot of public works projects, because what those financial advisors in the that work for the government do, they want to make sure that every dollar that gets spent by the government actually goes towards helping the public and not harming it. Okay. So let's do an example of this to see how this modification can be made. Okay. And so in this example, let's say that the city of Fullerton wants to improve traffic flow by adding more lanes to the road. Okay. And in particular, they want to focus on a particularly busy intersection. So at this intersection, they're basically gonna, widen the road out, and they have some options on how they want to split up these new lanes. Okay. Okay. And so the two options, one of them is to add an additional right turn lane. Okay. And so this would be a lane that they just put, at the very right. They just, raise up the sidewalk and then add an additional lane there, or maybe they just make the lanes a bit more narrow. Okay. So this one's going to be a little bit less intrusive and a little bit cheaper because of that. The other option is to add an additional left turn lane. Okay. And so, of course, since this is, in America, we drive on the right side of the road, adding a left turn lane is going to be a lot more intrusive because the left turn lanes are always in the middle of the road. Okay. And so that means you're going to have to shut down, probably the whole road for a while to, or at least a good chunk of it to add this lane. Okay. Okay. And so both of these options have been rated. And so both of them have their cost estimated. Okay. They also have their maintenance cost estimated. Okay. It's also been estimated, how much the construction on these on this road here is going to disrupt the public, right? Because as everyone that lives in Southern California knows, if you do any construction on the road, it's going to create some disruption, right, for at least a few months. Okay. And so we can actually estimate that that disruption in dollar amounts. Right, but then once the construction is completed, then it's going to become a benefit for the public, and so it's going to increase traffic flow. It's going to reduce accidents. It's going to help people get from point A to point B faster. It's less public complaints and so on and so forth. And so based on all those factors, in terms of improving, it's going to improve delivery speeds too for for the FedEx drivers, mailmen, stuff like that. And so all those things combined, we can kind of estimate how much benefit that's going to give to the public as well. Okay. And so we're going to give some numbers for that. Okay. All right, so let's put some numbers on this. And so the initial cost for the right turn lane is going to be $8.9 million. Okay. Whereas for the left turn lane, this is going to be 11.9 million. Okay, so it's a difference of $3 million. I'm using minus signs here to denote, which ones are costs. So for the right turn lane, it's going to have an annual maintenance of $150,000, whereas the left turn lane will have an annual maintenance of $225,000. Okay. For the initial public disruption, the right turn lane is going to cost about $900,000. Whereas the left turn lane, we know the construction for that is going to be a lot more intrusive. And so the city estimates that the initial public disruption is going to be 2.1 million. In terms of benefit for the public, the right turn lane is going to generate about $1.6 million of annual benefit each year. Whereas the left turn lane will generate more public benefit of $2.2 million. Okay, so there are the numbers. All right. And so for this problem, we're going to assume an interest rate of 10%. And we're going to assume an analysis period of 15 years. And so based on these numbers and based on the interest rate and the time period, let's use benefit cost ratio or the variation on benefit cost ratio to determine which option to go with. Okay. All right, so quite a lot going on in this problem, kind of a really long exposition, but we're going to go do the ratio from. All right, any questions on just the setup for the problem, any of the numbers? Okay. All right, and so of course, even though the extra car lanes itself aren't going to be generating any money, right? So the city's not earning any extra money from this. What we've done here is we've estimated these values. Okay, and so it's important to note that when you're doing these kind of public works calculations, any dollar amount that you have that that's been given with regards to the public, those are just estimates. That's not actually revenue. Okay, so both of these are just estimates. Okay. These are not real costs or benefits. Okay. Even though they're not, actual, no dollar amounts are actually being exchanged between people, this is just kind of the way that we kind of tangibly express or tangibly quantify the effect on the public, right? Because anytime you do a large scale construction project, it's going to affect the public in the surrounding area in a significant way. And so this is kind of the way that we just quantify it. Okay. Okay, and so since those two rows there are not real costs or benefits, it makes sense to put them in the numerator of this ratio. Okay. And so notice in this numerator here, I have both benefits and consequences to the public. And so, even though the initial disruption there is technically a negative cash flow, we're still going to put it in the numerator because they are effects of the public. Okay. All right, and so just like we did in the previous example, let's take the increment between them, right? So remember, we're doing a comparison, and so we're choosing either one or the other. And so in order to do that, we take the difference between the higher cost and the lower cost option. Okay? And so in this case, the higher cost option is the left turn lane. And the lower cost option here is the right turn lane. Okay. Okay. So let's go ahead and do that for this. Okay. All right, so let's start with the initial disruptions to the public. Okay. And so for the initial disruptions to the public, the left turn lane has an initial disruption of $2.1 million. Okay. Whereas the right turn lane has an initial disruption of 900,000. Okay. Okay, so this right here is public disruption. Okay. And then the next thing we're going to do, and because this is counting as a initial disruption, these two are already in present worth. Okay. And so I didn't write it here, but what we're computing here is the present worth of the public effects. Okay, so present worth of the pub. Okay. And so that the disruption, since that only really takes place during the construction period, they've already estimated it as an initial cost, basically. And so this is already in present worth format. Okay. Okay, so then we're going to do the same thing. So left turn lane minus right turn lane, but for the annual benefit. Okay. And so let's do the annual benefit for the left turn lane first. And so that's going to be 2.2 million. Okay. And since this is an annual benefit, this is something that's going to recur every year. We have to convert this to a present day sum. And so this is going to be P over A. Interest rate here is 10%. And the number of time periods there is 15. Okay. And so that's 2.2 million times P over A, 10%, 15. And of course, we're going to subtract the annual benefit for the right turn lane. And so that's going to be 1.6 million, P over A, 10%, and 15. Okay. All right. Go ahead and label this. This is annual benefit. Okay. And so we go ahead and plug the values in from the compound interest table. We perform all the arithmetic. And what we get is the present worth of all the public effects is going to be a positive 3,364,000. All right. And so that's the present worth of all the public effects. Now let's take the present worth of all the government costs. Okay, so we have two costs here. And so of course we have the initial cost as well as the maintenance. Okay. And so we're going to take the difference between these two as well. Okay. Okay. So first let's do the left turn lane. Okay. So the initial cost for the left turn lane is 11.9 million. Whereas the initial cost for the right turn lane is 8.9 million. Okay. This right here is all initial cost. And then to that, we're going to add the annual maintenance cost. So, both of these are considered together because they're paid out by the government. And so these are all, the government costs. Okay. And so the annual maintenance cost for the left turn lanes is 225,000. And so again, since this is a uniform series, we have to convert this to a present sum. Okay, so that's 225,000 times P over A, 10% and 15. And then we have the annual maintenance cost for the right turn lanes. So that's 150,000 P over A, 10%, and 15. Okay. Okay. All right, and so if we take, if we perform all the arithmetic, all the additions, subtractions, multiplications, we plug in the values from the compound interest table, what we get is a total government cost, or the increment of the government cost is going to be 3,570,000. All right. So now that we have all of this, we can go ahead and compute the ratio. Okay. And so the ratio here is going to be the present worth of the public effects divided by the present worth of the government costs. Okay. And so we take 3.364 million divided by 3.57 million. And what we get is a ratio of 0.942. And so, of course, you can see from here that this ratio here is less than 1. And so since this ratio is less than 1, then the best option to go with is the lower cost option. And in this case, the lower cost option is the right turn lanes. Okay. All right, and so that example kind of shows you how you can modify the benefit cost ratio for cases where you don't have strict money coming in or revenue coming in. And so here we modified it to be effect to the public divided by government spending. Okay. All right. Any questions on this? Okay. All right, and so that's, I think that's kind of all I wanted to talk about for benefit cost ratio analysis. But for the last, 25 minutes today, I do want to go over one more technique called break-even analysis. Okay, and I have one example for that. Okay. All right. And so in kind of the same spirit that we've been considering, break-even analysis is also a comparison technique, right? And so in break-even analysis, we're still doing comparisons between two different economic alternatives. Okay. But the question that we ask for break-even analysis is a little bit different. Okay. Okay. And so when we're comparing economic alternatives, sometimes it's useful to ask the question, at what point or at what, for what key parameter value are two alternatives equivalent? Okay. Okay. Right, because a lot of times there's one key parameter in the problem which can kind of sway the balance in between two alternatives. And so if we kind of form the analysis, or we kind of do the analysis around that key parameter, then we can kind of see it kind of gives us a different perspective on, which option is better than the other at which points. Okay. Okay. And so it's good to ask, at what value of this parameter, will we change our decision? And so that's the point of break-even analysis. And so with break-even analysis, instead of focusing on the cash flows, I mean, we're still focusing on the cash flows, but kind of the key, or kind of the what we're solving for in break-even is, what is the value of that key parameter? Okay. And so one example where this is used a lot is in this concept of called stage construction. Okay? Because oftentimes, whenever you're undertaking a very large construction project, kind of a big part of the planning process is, how do we want to stage it? And so, do we want to do a large portion first, or maybe we just do a small portion of it first, and then, have that go in operation, and then do the next stage. And you have to decide how many stages do we want, and all that stuff. And so it's quite complicated, actually. And so we're actually in the middle of doing such a thing for engineering college. And so, there's a big kind of renovation coming in the wings. It's going to take place over the next, 5-6 years. And we're currently planning out, how we want to stage it. So do we want to do both buildings at once? Do we want to do, make a side building? And so, it's still kind of under consideration a lot. Okay. Okay. And so a lot of times, the key parameter here is how quickly all the new facilities are going to be needed. Okay, because a lot of times, you're planning out a project for this huge new facility, but maybe only for the first 5 years, you're only planning on using just part of it. Okay? And so you have to think about it, does it make more sense to just build that one part first and do the rest later? Or maybe we try to save some money and then we try to build it all at once, because that's of course going to be a lot cheaper than calling the construction company to come twice. Okay. Okay, and so let's do an example here that kind of shows how this is going to take place. Okay. All right, and so consider this following construction project, which can either be done all at once or in 2 stages. Okay. Okay. And so here are the costs associated with each of those options. And so if we construct it all now, we construct it all at once, the cost is going to be $140,000. Versus, if we construct only the stage 1, And so if we construct only the stage one, just the first stage, that's going to cost $100,000. Okay. And so we would save $40,000. It's just that eventually we're going to need to complete the construction. And so eventually stage two will need to be completed. Okay. And if you and when we decide to do stage two construction, that's going to cost $120,000. Okay. The thing is, the thing that's complicated here is that, we don't need stage two right away. And so what we are saying is that in this problem, stage two is only going to be needed n years in the future. Okay. All right. So in this problem, what we're determining is, what's the break-even point for the value n? Okay. Okay. And so basically what we're saying is, which option we go with, whether we decide to construct it all now or wait to construct the stage two, it depends on how quickly we need stage two. Okay. And that's going to be the break-even point. Okay. And for this problem, we're going to assume an interest rate of 8%, just so I don't forget. Okay, so before we kind of start working on the calculations to solve this, let's kind of talk it through a little bit. Okay. And so, constructing it all at once makes a lot of sense if we need stage two, right away. And so if we need stage two relatively sooner, then it makes a lot more sense to construct it now. Okay, because it's $40,000 more expensive today, but if we're going to only wait 2 years to construct stage two, that's $120,000. And so that's quite a bit. Okay. And so if n is small, i.e. need right. But if n is large, and so let's say we don't need stage two for another 10, 12, 15 years, right? Then in that case, it makes sense for us to wait, because then that $40,000 that we save by only doing stage one, we can then invest that in the market and have that grow enough to basically cover the stage two construction. Okay. Okay. And so that's even before doing any calculations, that's kind of what we intuitively kind of understand from this problem. And so, let's see if the numbers and let's see if the calculations kind of support this, this idea here. Okay. And so we have two options here. And so, just like we normally do, let's convert all the options into into the same form of cash flow. Okay. All right. And so I'm just going to do present worth, just because present worth is, in the case for this problem is the easiest thing to do. Okay. And so the present worth of option one here is just going to be just the initial cost, right? So option one is to build it all at once. And so the present worth for that option is going to be $140,000. Okay. Okay. Meanwhile, for option two is the staged option. Okay. The staged option has an initial cost of $100,000. And then a future sum or a future cost of 120,000 taking place somewhere in the future. Okay, so this is P over F. Our interest rate is 8%. And the unknown here is N. Okay. Okay, so those are the two options. And so remember, the goal for break-even analysis is to, find the value of N where these two are equivalent. Okay. And so in other words, what we're going to do is we're going to plug in values of N into, the formula for present worth 2 until these two have the same present worth. Okay. All right. So let's go ahead and do that. And remember kind of what we kind of just said, kind of, informally here. Okay. So let's test a relatively small value of N. Okay. So let's plug in N is equal to 5. Okay. So 5 is relatively small. Okay. And so let's see what the present worth for this case is going to be. All right. So present worth 2 at N is equal to 5 is going to be minus 100,000 minus 120,000 times P over F, 8% and 5. Okay. We can look this up in the table. And this conversion factor right here is 0.6806. Okay. We plug that in and we get a present worth of minus $181,700. Okay. And so we compare this to present worth 1, right? And so, here, obviously, 181,000 is a lot lower than 140,000. And so it's going to be a lot more costly to the company to, to do the staged construction. Okay. And so in other words, if stage 2 were needed just 5 years in the future, then it's going to be, a lot more costly to do that. And so if N is equal to 5, then, we should go with we should build it all at once. We shouldn't stage it. Okay. Okay. All right. So now let's test a fairly large number. So let's do present worth 2. And so let's test N is equal to 20. And so if stage 2 is not needed for 20 years, 20 years is a long time, and so, you would think in this case that it would make more sense to stage it. But let's run through the calculations just to make sure. All right. And so when N is equal to 20, we have a minus 100,000 minus 120,000 P over F, 8% and 20. Okay. And so in this case, this conversion factor here is 0.2145. Okay. And so we punch all that in the calculator, and what we get is minus 125,700. Okay. All right. And so in this case, we get a present worth 2 that's greater than present worth 1. Okay. And so in this case, it makes more sense to stage it, because if stage 2, if we can wait 20 years to build stage 2, then this is going to be a lot more worth it, because then that $40,000 we save we can invest it and grow it and, you know, earn a lot more from that. Okay. And so the logic behind these two, you know, checks out. And so it checks out kind of with what we kind of initially said. But we haven't answered the question. And so the question for this is, you know, what's the value of n that makes it basically no difference whether we choose to build it all at once or wait. Okay. And so, you know, based on what we've seen already, you know, we know the value of n or the break even point is somewhere between 5 and 20. Okay. And kind of just based on the values of these, it's going to be a little bit closer to 20 than it is for 5. It's just kind of, you know, because PW220 is closer to 140,000. Okay. And so let's kind of check in the neighborhood of 15. So let's check PW2 n is equal to 15. Okay. So 100 minus 100,000 minus 120,000. And then we have P over F, 8% and 15. And so this is 0.3152. Okay. And so we plug that in, we get minus 137,824. Okay. So we're very warm, we're very close. So let's check one more thing. And so let's check 1 year above that. So let's check n is equal to 14. Okay. The conversion factor for n is equal to 14 is 0.3405. Okay. We plug that in and we get minus 140,816. Okay. All right. And so that's probably about as close as we can get. And so if you want to be sure you can, you know, well, you know, in this case, you know, we crossed over the break-even point. And so we crossed over 140,000 between 15 and 14. And so the closest number to this is actually going to be 14. Okay. And so what we say in this problem is that the break-even point is n is equal to 14. Okay. All right, and so 14, that's our breaker point. And so if n is less than 14, you know, it makes more sense to build it all at once. But if n is greater than 14, it makes sense to wait and stage it. All right, any questions on this example here? Okay, all right, so that's all I got for you today. And so we ended a little bit early, so maybe about 3.5 minutes early. And so, you know, we'll go ahead and call it here. And so remember, the midterm exam is on Wednesday, so please make sure to come here. Okay, so I'm not going to be on the Zoom room. And so if you join Zoom, you will be by yourself and probably wondering where everyone is. And everyone will be here taking the exam. Okay, so make sure you show up. If you have any other questions on the exam, what's going to be on it, or, you know, if you have any problems, you know, clarifying some concepts, I have office hours tomorrow at 4 p.m. and I have another office hours Thursday morning at 9 a.m. So we have I have two more office hours before the exam for you to come check in with. Okay. All right, so thank you everyone for coming today. You know, best of luck studying. You know, let me know if you have any questions for email or anything, and I will see you guys all on Thursday. Question, am I posting the solution for homework 3? Yes, and so I'm going to post it basically right after it's due tonight, and so you can expect the homework 3 solutions by midnight tonight. Yep. Mm-hmm.
With the strategy to figure out how to convert a recurring salvage value for an infinite n.
Yeah. So whenever you have an infinite n, the way to do it is with annual hash. And so
Okay.
there's no way to really do it with the present work. The N is basically infinity.
Okay,
And so for that, we're kind of relying on the fact that annual cash flow is a recurring thing.
okay,
And so in those cases, you know, you have, a salvage value. Let's say that, for this particular one, we have a life of, how many this is, 5 years, right? And so let's say we have an overhaul cost for, or you said salvage value, right?
yeah,
Yeah, salvage value. So salvage value is going to be at the end, right there, right? So it's just
or I think more what I'm asking is, so for one of the homework problems, I think it was, 2B.
Mhm.
It has a salvage value every 4 years.
Yep.
And is infinite.
Yep. Mhm.
How do we convert that to? Or to like in cash flow?
Yeah. Remember, so one of the benefits of annual cash flow is that you don't have to actually worry about buying replacements. And so what you do is you just analyze it for just one period of life.
Okay,
And so initial cost and salvage, and then just everything in between. And then, even if they have different lives, it doesn't really matter because, for annual cash flow, you're just doing one period.
okay,
And so the salvage value would just be at the end. And so you just do a basically an AO cap.
okay, okay.
Yeah.
And then what would the end be for that then?
It would just be the product life. And so, so the
Okay,
product life for that
okay.
one's 4 years, you do.
Okay, that's what I did.
Mhm.
And maybe I just did something wrong, like on another part, because it didn't line up with the solutions.
Okay.
I probably messed it somewhere else.
Okay. Yeah, if you're still struggling with it, just send me an email and then I can take a look at it. I might have I make mistakes sometimes too in the homework solutions, so it might have been something like that.
Thank you.
Yep. Mhm. All right, any more questions from Zoom? Okay, all right, so I guess I'll see you guys on Thursday.